Hey everyone. Today I want to take a look at using Node.js worker threads and the PM2 library to see how we can scale Node.js applications beyond a single thread, especially when we need to execute CPU intensive synchronous code. Now, if you haven't seen my last video on Node.js and how the event loop actually works, I recommend you watch that first. I'll leave a link to the video up above now where you can check it out. Otherwise, let's jump right in and see how we can get our hands dirty with Node.js worker threads and the PM2 library. I'll see you there. All right, so let's go ahead and get started by using the Nest CLI to initialize our new project. So if you don't have the CLI installed yet, you can simply run npm install-g to install it globally. And we want the nest.js/CLI at latest. So once you have the Nest CLI, we can then run nest new. And then I'm going to call this project workers-pm2. So you can run nest new and then choose the package manager you'd like to use. In my case, I'll use pnpm. So now that we've created the project, I'll cd into the directory and we can open it up in our code editor. So we have the default Nest.js application with our main.ts file being called, which is bootstrapping the application, creating our app, and exposing our HTTP server on port 3000 by calling app.listen to accept incoming HTTP traffic. And then we have our app controller, which is right now simply exposing the root get path. So we have a get route here, and this is simply calling our app service get hello to return some stub string data. So we can go back to our terminal and run npm run start dev to start up the application in development mode. So it will watch for our changes to our code. And then I've gone ahead and opened up Postman to execute some requests against our API server. So I've opened up a new request, a GET request, and we'll launch this at HTTP localhost 3000, and we just target the root path. And so we can see here we're targeting our app controller and returning that hello world string. So we can see our app server is running as intended. Let's go ahead and now start taking a look at using worker threads. Let's first go ahead and refactor our root get route, and I want to call this path blocking. So we're going to have two examples. We're going to have some blocking synchronous code that's going to run in our main thread to begin with, and I want to show you the effects of running this code, and then we're going to refactor it to then use workers so that we can move this synchronous blocking code to a worker thread and no longer block the main thread, and we'll see the effects of doing this. So let's go ahead and start implementing this blocking code. The first thing I'm going to do is change the method to blocking. We can get rid of the return type, and let's accept a query parameter. So to do this, we'll use @query from Nest.js common, and I want to accept a query parameter called CPU time milliseconds. So this is essentially how long we're going to ask the given request to wait inside of our blocking code. So we'll call this CPU time ms, and by default this will come in as a string. So then I want to call app service.blocking and then pass in parse int, which will convert a string into a number. So we'll pass in the CPU time milliseconds to parse it into a number. And now let's go ahead and actually implement this blocking code in our app controller. So it's going to be quite easy to do this. We'll simply rename the function to blocking. And now it's going to take in, as we know, that CPU time ms, and this will be a number. So let's go ahead and add this, and then we can get rid of our return type. And now inside of the actual function, I want to create a const, and we'll go ahead and call this start time and set it equal to the current date.now, which is the current milliseconds value of the current code time. And then I want to execute a while loop. And so we know that executing a synchronous while loop in Node.js is going to block our main thread, which in this case is exactly what we want to do. So let's go ahead and while date.now minus start time is less than CPU time millisecond, then I simply want to keep running this loop. So what this is actually doing is it's running the loop until we've reached CPU time milliseconds, and and then it's exiting the loop. So by doing this, we're essentially blocking the main thread in Node.js for this given amount of time. And of course, we know that in Node.js, since it's single-threaded, it's not going to be able to do any other work like serve other requests. So let's go ahead and actually see this in practice. I'll go ahead and now launch another GET request, and this will now be @/blocking, and we'll pass in a query parameter. So we'll use $CPU time ms and set this equal to 10,000. So for 10,000 milliseconds or 10 seconds, I want the CPU to just sleep. And I'm gonna also copy this request and paste it into a new tab. So firstly, let's just go off and send it one time so we can see the request run. And of course, we can see the request hanging because it's in that while loop right now. And now it's broken out. So exactly at 10.02 seconds, we've returned a status 200. Now, the key thing about this right now is if we send this request and then immediately in our second tab execute another request, we can see that it's hanging right now. And we can go back to the first one and wait until it completes. So this one completes in 10 seconds. And the second request here didn't even finish up until 18 seconds or so. Even though we executed it pretty much exactly at the same time as the first request, it still took much longer to actually complete. And that's because while this first request was actually running and blocking the CPU, this second request couldn't get serviced yet and enter into our actual while loop because this first request is blocking the main Node.js thread. So this one completes, and as soon as it completes, the second request can now start processing. Now, this is the danger of using synchronous blocking code in Node.js. In many applications, this is going to be asynchronous I/O. So for example, if we're talking to a database or we're making some sort of network request, well, Node.js uses the event loop to free itself up from that task and do other work like service other requests in the meantime. However, since we're executing the synchronous code here, the event loop can't do its job. And that's what we want to now try fixing with worker threads. We want to offload this heavy synchronous work that's blocking our one Node.js thread and the event loop from doing other work like servicing other requests. We want to offload that work to a new thread using a worker thread. Let's go ahead and see how we can do that next. Now, before we move on, another thing I want to show you is if we open up a new terminal window and enter in top, we were going to get metrics back to see the CPU usage for each of our processes running on our system. So with top running, let's go ahead and send another blocking request at our API server. And as soon as I send this, you can see our node process here using 100% of the CPU allocated to it. Now, the reason this is happening is because we're executing our while loop, which is synchronously running this code on the main thread and occupying 100% of the CPU on that thread. Now, we only have a single thread. Node.js is single threaded by default, so we can only use up to 100% CPU. And that's what we're doing. We're using all of the CPU on that one while loop, and that's why we can't serve any other requests in the meantime. In our app controller, I'm going to go ahead and create a new get route, and this is going to be called worker. So we'll create a async worker function, and this will again take in that same query parameter of CPU time ms. We'll call it CPU time ms, and it will be a string value. And now I want to return this.appService.worker, and again pass in that parse int call to turn the CPU time ms into an actual number. And then we'll go to the app service to actually implement this function. So let's go ahead and do that. We'll have a async worker function that takes in the CPU time of type number now. And this is an async function because I want to actually return a new promise. So we're going to return a new promise from this worker function that's going to actually resolve once the worker thread has completed its processing. So we still need a way to wait for the request to complete, and by wrapping this operation in a promise, we can do just that. So inside of the promise callback, we get the resolve function and the reject function, which we can call depending on the outcome of our worker thread. So now inside of this promise, let's go ahead and actually create the worker. We'll create a new const called worker and set it equal to new worker. Now we're going to import worker from worker underscore threads, and you can see the import up here. And this now takes in a file name. And so the file name is going to be the actual JavaScript code that's going to get executed on the worker. So to do this, I want to create a new directory in our source folder called worker, where we're going to keep all of this code. And the first thing I'm going to do is create a new constant to actually host this worker thread file path. So let's create a config.ts. And in here, we can export the const called worker thread file path. And this will be the current directory name. So let's wrap this in a template literal and actually escape the current directory name. So this is a special keyword that we can use in Node to get the actual directory name that we're in. And then now that we're in this folder, we're simply going to target worker/js. And this is going to be the JavaScript file we're going to manually create to host our worker logic. So let's create this file now. We're going to create this worker.js. So this is going to be the Node.js code that the worker thread's actually executing inside of the new thread. So let's create this async function called run. So when this file is actually run by the worker, it's immediately going to call our run function. And now inside of here, we can implement our synchronous work. Now I made this function async because I want to show you how we can actually get access to the Nest.js dependency system within inside of this worker thread. To do this, we can take advantage of Nest.js standalone application. So we're going to create the Nest application actually outside of our running app, which we can do perfectly fine thanks to the Nest factory. So let's create this app, and this is going to be an await call to Nest factory dot create application context. So now we can pass in our root app module. So let's firstly go ahead and refactor our import to the Nest factory to be from Nest.js core, and then we're going to manually import the app module from just one directory up and reference the root app module. So this is going to actually create our Nest.js application outside of our other running app, and then we can get access to, for example, our app service by simply calling app.get. And by calling app.get, we can actually get any provider in our application that you need to actually implement this worker logic. So in our case, let's actually get access to the app service, and then we'll simply log out that we're in the worker thread. So the worker thread got data, and I want to show you how we can actually receive data from the main thread. So to do this, we'll simply reference the worker data variable that we import from worker threads. So this worker data is going to actually be the data that was passed over from the main thread. So let's log it out. Next up, let's actually call appService.blocking on this worker thread, and then I want to make sure that we pass the CPU time milliseconds in this worker data object. So that's what it's going to be. It's going to be an object that we're going to provide. So let's simply reference the CPU time ms on it. And then finally, in order to pass data back from this worker to the main thread, we take advantage of the parent port. So we can call post message on parent port and then pass in whatever data we want. It can be an object, it'll be serialized, or in our case, I just want to pass the worker data back to the main thread. So you can do your processing here, receive data from the main thread thanks to this worker data, and then pass the information back to the main thread using parent port. So let's go back to the app service, where now we need to actually provide the worker we created with the worker thread file path. And let's go ahead and correct this to make sure it's a lowercase a in path, and then we'll do the same in our application and update the import. So this is all we need to do to actually create the worker and spin up a new thread to do work on it. However, we also want to pass the worker data. So to do this, we have an options object where we have the worker data object that we can populate. In this case, we just pass in the CPU time ms on it. However, you can pass in whatever data your worker needs. Now we're going to go ahead and attach callbacks on this worker, which is how we can actually listen for events that happen in the worker thread so we can respond and of course eventually resolve this promise to the main caller. So let's call worker on where we can listen for an event. So in this case, we have access to the message event. So whenever we receive a new message from the worker, we get it in this callback. So now that I have the message, I'll simply log out main thread got message, and let's include the message that we got sent back. So we know this is going to be the parent_post message call that sends it, and we're simply passing in the worker data. So that worker data will be passed to this callback. So after we log it out, we're then going to resolve this function. So after we've executed the blocking code inside of the worker, sent the data back, we're in this callback, and then we can finally resolve this promise to complete the request. I'll also pass in the message to the resolve function, so we actually send back the worker data to the response when we send it back in our HTTP route. Because remember, this is simply resolving the promise that we're returning back to our Nest.js route handler. Now let's also see how we can listen on errors. So if an error occurs in our worker, we can simply log it out and we'll say console.error and say worker threw an error, and we can log the error out, and we can also reject the promise with the error. So if an error occurs, this promise will be rejected and the caller will know that error occurred in the worker. Finally, we can listen to the exit command on the worker to specify the code, the exit code from the worker, and we'll simply log out that the worker did exit with code and pass in that code. So now we have this completed worker function, and we're returning a promise that resolves when the worker thread actually completes its processing. Importantly, we need to make a change to our TS config so that this JavaScript code is actually compiled and included in our dist directory. So simply go to your TS config, and we need to add a new property called allow.js and set this to true. Now, if we go ahead and restart our development server, we should see our code gets recompiled. And now if we look inside of our dist directory, in your worker directory, you should have a worker.js. Okay, so now back in Postman, I've updated all of our actual route calls to point to /worker now. So I have /worker, same CPU time ms of 10,000, so 10 seconds, and I have 3 requests occurring here. So let's go ahead and trigger each request one after the other and see the effects now. So the request just finished, and if we actually look at the response times for each request, we can see that they've each completed in around exactly 10 seconds. And this differs greatly from our blocking method. So remember, if we change the call back to blocking, for example, and we execute the same exact example, we will see a completely different result. So let's go ahead and execute this now. So you see for the blocking example, the first request completes in 10 seconds, the second request about 20, and the third request gets up to 27. So you can see this cumulative effect of the requests stacking on each other, essentially getting processed one after the other, even though we requested them all at the same time. Well, we only have one thread that's completely blocked in each request, so we can't do work simultaneously. However, in the new updated example of using the actual worker, the story is completely different. Since each time we execute a new request, we're actually creating a new worker underneath the hood and doing this work in completely separate threads. So we have 3 separate threads going here with doing this heavy synchronous work, and they're able to be executed in parallel, and that's why they return in around the same exact time. Now, even more interesting to look at is if we execute these requests one after the other and then switch back to our top, you can actually see the CPU for our Node application is now close to 300%. And that's because, well, we have 3 threads that are actually running simultaneously, each using 100% CPU. So the cumulative total of all the threads is going to be 300%. So you can see the CPU usage and how it correlates to our actual throughput, since this work is now being executed in parallel on these 3 threads. So hopefully you've learned a lot about how worker threads can help to parallelize your heavy synchronous work in a Node.js app. Now, most of the time in your application, again, most of this work is going to be asynchronous I/O, like network requests, reaching out to some server. So you don't need to really worry about worker threads when it's asynchronous I/O. And that's because when you execute asynchronous I/O, Node.js will simply register the callback associated with that call and do other work in the meantime. So it doesn't actually take up CPU. And that's how Node.js is able to scale so well on just one thread. It can do other work while it waits. However, when you have heavy synchronous code like this while loop, for example, then it makes a lot of sense to actually use different threads on your app so you don't block this one all-important Node.js thread so it can serve other requests. So next up, I want to show you PM2. So PM2 is a daemon process manager that helps us to keep our Node.js application online and utilize multi-core architectures. So as we know, Node.js is only going to run on a single thread. However, PM2 is a third-party library that utilizes the Node.js cluster module. Now, the Node.js cluster module, I'll include a link in the description where you can read more about it, is essentially an API that allows us to spawn multiple instances of Node.js over multiple threads and distribute work between those threads. Now, they're a little bit different between worker threads because they're not actually spinning up a whole new thread. We're actually spinning up an entire new process. So it's a bit more heavyweight, but it allows us to distribute work between these processes. And so thanks to PM2, we can use its cluster mode to actually create a networked Node.js app, or in our case, an HTTP server that's going to scale across all CPUs available without any code modifications. So it's going to allow us to increase our throughput and performance depending on the number of CPUs. So let's go ahead and take a look at how we can use PM2 to take advantage of the hardware that our system is running. Even though Node.js is single-threaded, we can still scale it to all available cores. So let's go ahead and firstly install PM2. So I'm going to use npm install and install PM2 at latest. And this is going to be -G to install it globally on. So with PM2 actually now installed, it's super easy to actually start up an underlying Node.js app with it. All you have to do is run PM2 start, and then we provide the path to the actual application. So in our case, we know in our dist directory and the main.js is where our application is actually living. And then we can specify the -I option to enable the cluster mode. So what that's going to do is it's going to tell it how many actual instances of our app we want to run. And this is obviously going to depend on the number of cores we have. So we can pass in the max option so that PM2 will automatically detect the number of available CPUs and run as many processes as possible, one for each CPU. So I've gone ahead and run this command, and now you can see that it's actually started our app, main.js, in cluster mode, and you can see it's spun up 16 different processes of our Node app. And that's because I have 16 cores running on this MacBook, so it's actually spun up a Node.js server, well, in our case, the same Node.js server 16 times, one for each core, and PM2 will automatically listen on the same exact port. So in our case, it's still localhost 3000, but it will then load balance those requests it receives to the available processes. So if we send 100 requests at our server, it will evenly distribute them between all of these available processes. Now we can see this if we simply run another GET request at localhost 3000. I'm still able to execute the request and nothing has actually changed. So I still get a response back after 10 seconds, and that's because our PM2 process is actually running the app. And if you want, you can run PM2 ls at any time to see the state of our application. So I actually want to show you these processes in action. So to do this, we need to generate some sufficient load in our application. So I want to send a lot of HTTP requests concurrently at the app and show them being load balanced between these available processes. So to do this, I'm going to take advantage of Artillery, which is a simple Node.js based load testing tool. So let's create a new artillery.yaml file in the root of our directory, which is essentially just going to allow us to define a test in YAML format. So we're going to have a config key and we're going to have a target. So the target is essentially just the endpoint we're going to reach out to. So in our case, we know it's localhost 3000 / blocking and specify a CPU time ms of something more conservative. So in our case, just 100 milliseconds since we're going to send a lot of requests. So then we have the phases section where we specify the duration of the test. In our case, I'll say 60 seconds, and then the arrival rate. So this is how many concurrent requests are being sent at once each second. In my case, I'll just do 50 requests. So now we have the basic test set up. We need to actually define some scenarios, which is essentially just the different sections of the test. So we have a flow block here, and within this one, I'll add a loop, and in the loop, I'll add the actual GET request we're making. In this case, we're going to access the root of this URL. So since we're just calling this URL itself, we don't need to provide anything else to this scenario section, just a basic block here to get the test to actually run. And finally, don't forget that the URL block here should actually be indented one more. Now, to make sure you have Artillery on your system, make sure you run npm install-g artillery at latest. And finally, to actually run the test, I'll run artillery run and specify the artillery.yaml. So now you can see that our test has actually kicked off and we're now launching requests at our backend. So now we can actually see the statistics for our artillery test, including the median and mean response times for our given requests. So while the test is running, I want to go ahead and run top in another application tab. And the reason why I want to do this is because you can actually see all of our node processes that PM2 is actually running and the underlying CPU usage for them. So you see how they're actually very similar for each process. And that's because PM2 is distributing these incoming requests from Artillery and load balancing them to all of these node processes. So hopefully you've learned in this example of how to scale our Node.js application natively. So even though it's single threaded, we can still take advantage of multiple core machines by using something like PM2 and the underlying Node.js cluster module, which allows us to scale our application horizontally and distribute and load balance these requests between them. Now, a lot of people may ask, how is this different from using Kubernetes and, for example, running a single Node.js pod and then scaling that pod horizontally so you have many of these Node.js pods? And the answer is it's really not any different. It's the same process. We're just scaling out the app horizontally and load balancing the requests to them. In that case, it's a simple load balancer that's doing the load balancing. So it's just two different techniques to get this kind of horizontal scaling of the underlying compute. So I hope these two examples have been very helpful for you to see how we can actually scale Node.js beyond a single thread. Thank you so much for watching, and I'll see you in the next one.